It's a pleasure to introduce Bill Moses. He's a PhD candidate at MIT. His background is ECS and physics and engineering. He's been doing a lot of compiler work over the last several years. And maybe most notably among that, it was the lead author of ch-Enzyme, which is a really cool tool. He's going to tell you all about how ch-Enzyme works. It's built on LLVM, opens up the ability to use automatic differentiation in a lot of new places. He's a CSGF fellow, so that's a Department of Energy fellowship. And beyond that, take it away.
Cool. So hi, everyone. First off, if you have any questions, feel free to just chime in or put them in the chat. And worst case, we'll go some extra questions at the end of it. But yeah, so I'm going to be presenting our work on ch-Enzyme. That's high performance, cross-language, and parallel automatic differentiation, which is joint work with a whole host of people. Without any further ado, let's begin. So computing derivatives is key to many algorithms, be it in the machine learning community or the scientific computing community. In machine learning, this is most common if you have a neural network and you want to go train it, you'd run the backpropagation algorithm, which involves computing the derivative of the laws with respect to all of the weights. In scientific computing, this is quite common in various types of simulation. So if you've ever seen a physics equation with a derivative in it, that usually means that you might need to take a derivative of some sorts in your actual simulation. In particular, when you want to work with especially large code bases, or in particular, if you have a program which generates code automatically, it may not be the most desirable thing to be able to manually write these derivative functions. And in fact, if a lot of this code is indeed dynamically generated, it can even become impossible to generate it all by hand. As such, the community has developed tools to be able to generate these requisite derivatives automatically. So there are three existing approaches for performing automatic differentiation. The first approach is to rewrite everything in a new differentiable domain-specific language. Some of these you might have heard of, such as TensorFlow, PyTorch, JAX, or Diffie. And the essence here is that you want to create a new language where every single primitive and everything in that language is explicitly designed to be differentiated. This can end up working quite efficiently if the domain-specific language matches exactly what you want to do. However, if it doesn't exactly match what you want to do, it can end up being quite slow. And more importantly, if you have an existing code base and you want to go ahead and differentiate that or use it inside of one of these approaches, it means you have to spend your time not thinking of the high-level algorithm or the high-level utility that you want to do, but instead reading that entire code base into the new DSL. The second approach is known as operator overloading. Examples of this include adept inside of C++ or JAX inside of Python. In essence, the idea here is rather than creating a new language where everything's differentiated, let's create new versions of specific language constructs that are specifically designed to be differentiated. So in adept, you can have the notion of a double inside of C or C++, and instead of using your regular double type, you'd use this differentiable A double type, and all of the operations built out of that are now differentiable. Similarly, if you're using JAX, if you have code that just uses NumPy operators, such as, say, numpy.sum, you'd replace that with the equivalent jax.sum. And then that operation is known to have a particular derivative. This still, however, while a little bit nicer than rewriting all of your code into a DSL, still may require some amount of rewriting to be able to use non-standard versions of these utilities. Specifically, doing the rewrite alone from NumPy to JAX or double to A double is a little bit of work, but more importantly, these libraries don't necessarily support all the types of operations that you want to do. So for instance, JAX may not be complete over all of the NumPy code, and moreover, you might have some code that's not written in NumPy, which means that you can't differentiate it. More importantly, these approaches also tend to be dynamic on a performance front, meaning what they do is for every single operation that you'd originally run, it would store in some extra map what instance that you ran, and then interpret those values in the reverse pass, which means that this can end up being quite slow. The third approach is known as source rewriting. An example of this is known as Tapenade. In essence, what happens here is this external tool would take as an input your actual program, and it would statically analyze it and output you a new source file, which contains the gradient or the derivative of that function in that source language. It often requires a fair amount of work to be able to do this, such as the fact that it has to re-implement all of the parsing or language semantics, which means that it's difficult to use with more complex languages. As an example, the state-of-art approach here, Topanot only works with C and not the more complex C++ for all of those features. More importantly, it also requires all of the code you might want to differentiate to be available ahead of time. So if you have something in an external library that you may not exactly know which version is going to be used, or just generically you have some code that is not available in source form, you probably won't be able to go differentiate it with a source rewriting approach. However, because it has the ability to operate at the source level and to be able to do all of this work statically, it can work quite fast in practice. Generally, all of these three approaches follow the same pipeline. So we start off with some original code in our language of choice. We run them through our favorite type of AD tool. We then get another code in that same language of choice, and we go through the traditional compiler pipeline, which involves lowering to some intermediate representation, optimizing that code, and creating a final binary. Let's see how this existing approach works in practice for a sample vector normalization code. So here I have this code that normalizes a vector. I have an input array, I have an output array, and for all elements in these two arrays, I say the output equals the input divided by the magnitude, where the magnitude runs in O of n time, and as such, the total function runs in O of n squared time. Now, any compiler worth its salt will realize that the call to the magnitude function doesn't need to be called once per iteration of the loop, but instead can be hoisted outside the loop, doing it once, and thus reducing the runtime from O of n squared down to O of n, a dramatic speedup. So now, after optimization, let's talk about what it would take to go ahead and differentiate this. So this doesn't necessarily mean that we're working in any particular tool, but just theoretically, if we were to go down this pipeline. So we previously did the optimization. Now we want to go ahead and differentiate it. The way that this differentiation algorithm works is to basically mirror all of the same instructions you had in your original program and create the corresponding derivative versions in reverse order in the reverse pass. So after optimization, since we have this mag function outside the loop here, we'd have again our for loop with the gradient magnitude function outside the loop. Since the previous code that we were before differentiation was in O of n time, the code after differentiation here is also O of n time. But let's imagine we did this in the opposite order. Since all of those existing AD tools have to first run differentiation before any optimization, how would this work in practice? So once again, we have the call to the magnitude inside the loop. We'd run those existing AD tools, which because this is currently inside the loop, we'd have the derivative again, or the gradient mag inside the loop. But when we go ahead and now try to run optimization after the fact, we can't actually move the call to the gradient magnitude function outside the loop. And the reason is it's effectively stuck because it uses this variable local to the loop called dres. And since that variable is local to loop, you can't move it outside safely. And thus, as a consequence, if you were to differentiate instead after optimization, unlike all of those tools, you can end up with the asymptotically faster gradients shown on the top. So the key idea behind Enzyme is that by being able to perform AD at the low level, we can now work on optimized code because it allows us to run after and alongside those existing traditional optimization pipelines. So we can take code in a variety of all of these languages since they go down to the same intermediate representation, namely LLVM, first optimize, then run AD, and just for extra kicks, we can run an extra round of optimization after the path. So what is LLVM? It's effectively a cross-platform version of assembly that is used in a variety of different languages and thus has a variety of what are referred to as front ends. Moreover, it also can produce code for a variety of different architectures, be it CPUs, GPUs of different sorts, what have you. Most importantly, it also has well-defined semantics. So unlike some types of assembly, it's very well-defined what exactly every one of these operators will do. And most importantly, it is a large collection of optimization passes and analyses that we can use to optimize and analyze our code. So let's take a quick look at how this might work on a sample code in practice. So on the left, we have the C code for ReLU3, which basically says if x is greater than 0, return x cubed, otherwise return 0. If we wanted to go ahead and use Enzyme to get the derivative of it, we would use something like here on the bottom. So we'd call this magic function Enzyme autodiff. The first argument, we would have the function we want to differentiate, that's ReLU3, and then the arguments that are required by that function. If we now were to lower this immediately and look at what this looks like at an LLVM level, we would have this code on the right. So we define the fact that we're making this function value 3. We'd compare if x is greater than 0, and if so, go down the true branch, which computes x cubed. And if not, we would go down the default branch, and then depending on which one of those branches we went down, we would pick the corresponding result. First, what Enzyme does when it takes in this code is it deduces what are referred to as active instructions. So that's to say, which particular instructions are necessary to compute the actual derivative, or moreover, which ones actually would end up changing the derivative if these values were to end up changing. In this case, the active values and instructions are the argument, the call to POW, the resultant fee, and the return. Next, what Enzyme does is it goes ahead and allocates and zeros shadow memory for the active values. In essence, what this shadow memory represents is it's the current result of the gradient, which to begin with, we're going to accumulate all the results in there. So that's why we zero initialize these. We then go ahead for all of the active instructions in our original program, compute what are referred to as the adjoints for those. So you can think of these somewhat as the derivative propagation rules. So if we take a quick look at this particular example on the left, so we have x cubed, for instance, and then the derivative we want to propagate is 3 times x squared, which matches what you may have seen in your calculus class. Doing a bit of optimization on top of the result there, and we get something that looks really nice. And if I were to handwrite this back into C, it looks effectively like the optimal handwritten gradient in this case. Of course, doing everything at this low level, while it has definite advantages, isn't necessarily free. And there's reasons why this hasn't been explored historically. So traditionally, this low-level code lacks some information that may otherwise be necessary to compute adjoints. So say I have 2 generic pointers to a source and a destination, and I want to copy 8 bytes from the source to the destination. If I knew for a fact that these 8 bytes represented a single 8-byte or 64-bit floating point value, then there's one particular algorithm that I would use for the reverse pass, which is to just do one 64-bit add. If instead this 8 bytes actually represented 2 distinct 4-byte or 32-bit floating point values, then the corresponding reverse pass would be doing 2 32-bit floating point adds. And as these 2 additions are fundamentally incompatible with each other, if you wrongly deduce this to be a float when it was a double or vice versa, you'd end up with the incorrect result. So the way that Enzyme remedies this is by introducing a new interprocedural data flow analysis that goes and deduces the underlying type of all the data in the program. So we define what's referred to as a type tree, in which for every single value in the original program and a set of memory offsets into that value, the corresponding type that it represents. So let's take, for an example, this sample code on the left. So I've defined the struct myType that at the first sort of offset here contains a double, then a pointer to an int. Then I'm going to define, I have my new variable x, which is a pointer to a myType. So in this type tree style representation, first x we know is a pointer at offset 0. Within that pointer at offset 0, first is a double, then is another pointer, finally to an integer. So by initializing all of the various values with types of information that we can deduce immediately from the front end, and then running a series of fixed point updates through the instructions, we can deduce all the types we need to be able to perform the correct adjoints as alluded to on the previous slide. A couple of other key points of Enzyme is that some of these adjoint propagation rules may also require values from the original or forward pass. So as an example, say you wanted to take the derivative of x times y. You know that the derivative of y here, for example, is just x, and the derivative of x here is just y, meaning you need the original value of x or y. So if those were to be overwritten or otherwise unavailable, you need to preserve them or cache them somehow for the reverse pass. And Enzyme, for all of these values that it deduces are necessary, it will allocate memory in the forward pass to store the value. And if these happen to be inside of loops, it will store an array that it will try to keep as a static array for performance if possible. But if it can't deduce the static bounds of the array, it will otherwise do a power of 2 reallocation. From here, we went ahead and said, let's go and see how this runs in practice. So we took a standard benchmark suite from Microsoft called ADBench, which has a large or 4 different machine learning focused benchmarks and a couple of others of technical interest from the scientific computing community. So first we have our regular enzyme pipeline, which runs optimization, then automatic differentiation, then another round of optimization. Then we have 3 pipelines which are designed to emulate the standard way that automatic differentiation is run historically. So first we have the reference pipeline, which tries to be enzyme as if it were those other tools, which is to say first run automatic differentiation before any other optimization, and then 2 rounds of optimization. And then finally, we have the fastest source rewriting tool called Tapenade, and the fastest operator overloading tool called Adept. And you'll notice here, we call the 2 rounds of optimization for all of these. And the reason for which is because some of these optimizations are not necessarily idempotent. So if you were to run, as an example, a particular optimization on a matrix multiply, running the same optimization again could result in a performance speedup or slowdown. And to prevent any of that from coming into play, we run all of these pipelines with 2 rounds of optimization. So let's take a look at how this performs in practice. So here I've plotted the relative speedup of all of these tools. So in essence, higher is better. So first, let's compare enzyme with a reference pipeline to see how our hypothesis, how optimization comes into play. So for most of these cases, we see that there's a fairly sizable speedup. So that's the LSTM case, the bundle analysis, the GMM, the Euler, the RK4, all see a noticeable speedup. F15 Brussels Rater were already very highly optimized. So doing additional optimization to begin with didn't result in as much of a speedup, and you see they're effectively the same. Overall, enzyme has a 4.2x faster runtime than the typical reference pipeline, showing that on average, this can make quite a performance boost. If we now look at how these existing tools work, that's the Tapenade and Adept. In particular, if we look at the LSTM or bundle analysis tests, we see that the reference and Tapenade pipelines are roughly equivalent in performance, which implies that the ability of enzyme to get a speed up over these existing tools largely comes from its ability to do optimization first. Now, there are some differences that aren't simply in being able to apply optimization first. These are different caching infrastructures, different overall pipelines, but with a little bit of a grain of salt, it makes sense that this is why it comes into play. Adept tends to be a little bit slower because, as I mentioned earlier, they have to store all the instructions and then dynamically go interpret what occurred there. You'll also note that there is an X on the Euler and RK4 test because these are both in C++ using the ODint library. And Tapenade, while a source writing tool, is able to be quite fast, but isn't able to handle C++, and thus doesn't work on these 2 cases. Specifically, we provide 2 nice utilities for anyone wanting to use enzyme to integrate external code into their existing machine learning or scientific computing pipelines. So we have bindings for both PyTorch and TensorFlow that allow you to import arbitrary external code and then bring it in as a layer that's fully usable inside of your existing neural network, as an example. From here, the next big question we tackled is how can we use automatic differentiation on GPUs? So it turns out that this has been a historically quite hard problem and that prior work has not been successful of getting reverse mode AD of generic existing GPU kernels. And this is fundamentally for 3 reasons. The first of which is doing a naive reversal of that parallel control flow can lead to incorrect results from races that are created. The second reason is that the complex performance characteristics of the GPU itself make it quite difficult to synthesize efficient code. And the generalization of this, in which that there is more precise resource limitations on the GPU in contrast to the CPU, can even stop the generated code from running at all. So diving into each of these, the first challenge was that parallel automatic differentiation in general can often be quite hard. So if we take this code on the left here, which takes a parallel for loop, and for all indices of the array, sets that array to equal some input value, we notice that all of these iterations read from the same variable val. And in essence, there's a race reading, but it's totally fine for all of these to read the same value simultaneously. However, because automatic differentiation flips reads and writes from the forward to the reverse pass, when we look at the corresponding parallel for in the reverse pass, where we have previously had a read writes on val, we now have a write race on dval. And since all of these threads are simultaneously trying to update it, you can get an incorrect result due to this race behavior. The second big thing that comes out of the GPU is that there's this complex memory hierarchy that is really crucial to creating performance. So as a brief intro to that, I'm going to talk about the three types of memory that you might see. So first of all, there's registers at the lowest level. There's relatively few of them. They exist per thread, but they're also the fastest possible way you can do computation. The second thing more in the middle here is what's referred to as shared memory. They're shared between blocks. There's, say, orders of kilobytes of these. Similarly to the registers, using too much of this can limit your parallelism. It's slower than a register, but it's still decently performant, and it has a little bit more memory for use. The final bit is referred to as global memory, which exists across the entire GPU. It tends to be on the order of kilobytes and quite slow, but if you have a large chunk of data, you can end up putting it inside of global memory, whereas you probably can't get away with putting it inside of either a register or shared memory. So the way we resolve some of those race and complex performance characteristics is to look at the problems together. So specifically, we say, let's try to resolve races in a way where whatever type of memory we had, we keep the same performance characteristics or the same speed roughly per type of memory. So if we have that really fast register, or generically some sort of memory which we know is thread local, since it's thread local, there won't be a race, and we can just use a simple non-atomic load and store to increase the value quite quick. If we have something in between, so for instance, we know that there's the same memory location used across all threads, we can use a parallel reduction, which not nearly as fast as the naive non-atomic load and store, still can be reasonably performant. And finally, if we don't have any of these properties, we go to something which is always legal as a fallback, and that's to do an atomic increment, which, if we don't have some of these nicer cases, tends to fall in the category if we already had slower memory to begin with. So we roughly maintain the types of performance characteristics we had earlier. The final big problem that had to be resolved is dealing with these specific types of synchronization. So within the GPU computing infrastructure, there's this notion of a sync threads, which guarantees that all the threads before the sync threads are completed before all of the code after the sync threads starts executing. This sync turns out to only be necessary if A and B could access the same memory, since if they access completely different things, you can't see a difference if there is no sync threads there. We then go ahead and say, if we assume that the original program is race-free, let's try to prove that doing a sync at the corresponding location in the reverse pass will ensure correctness of the overall algorithm, given the types of primitives we talked about earlier. And we go ahead and prove this by the different cases that can occur of you have a read first and then a write after the fact, and vice versa for all of these. If you're interested on the specifics behind this proof, please come to our supercomputing talk in November or read our paper. From here, we then said, okay, if we go and run it, what comes out of it? And it turns out that GPUs, even with taking all of this into account, can often be quite slow for non-highly optimized programs. So specifically, if we were to do the same experiment we did earlier for the CPU program, where we were to run the reference pipeline, that's Enzyme with no pre-processing optimization, Enzyme, or these GPU gradients, would have to cache a huge number of values. And the fact that you have to cache these values means that the program slows down quite a bit, because these values end up usually having to be cached in global memory. So if you have a very large number, you'll end up bottlenecking your program based off of the number of things you have to cache, if you can even fit all of that in GPU memory at all. Much like we saw earlier for the comparison with reference, running those pre-processing LLVM optimizations can reduce that overhead. But for the GPU case, unlike the CPU case, those existing optimizations aren't sufficient. So what we did is we introduced novel GPU-specific and AD-specific optimizations that can end up speeding up the code by several orders of magnitude. So a very simple example, suppose we have this code on the right. So we have a for loop taking in these two vectors, x and y, summing them up, and using them in some sort of function. We don't really know or care what it is. The corresponding reverse pass for this would be to do the gradient of the overwrite, then in reverse order for all iterations of that loop, do the gradient of the use with that sum. So we need this variable sum at the corresponding location in the reverse pass. And since we see that X and Y are themselves overwritten by this overwrite, we need something to be able to preserve whatever that value of sum ends up being for the reverse. So the first and naive thing that you can imagine doing is saying, for all pieces of memory that are overwritten between the forward pass and the reverse pass, just store them. So then if you actually need those values again for the reverse pass, even though they're overwritten, you have those values again. So we end up storing two arrays inside of X cache and Y cache. And indeed, we have the variable sum that we can use for computing our gradient of the use function. However, if we look at the data flow graph, which is shown on the left here, so I've highlighted in red the values that are overwritten, and I've also highlighted in blue the values that are actually required for the reverse pass. And so long as we're able to compute all of these blue values that are required for the reverse pass, it doesn't matter which of the other values in our graph are kept. So rather than computing X and Y, we can instead just compute sum. So if we cache sum and then just use sum cache, we can reduce the amount of memory by a factor of 2. In particular, as a heuristic to go solve this problem, we run a max flow min cut to deduce the minimum number of values inside of this graph to be able to reduce the number of things we need to cache. Overall, when taking all of these optimizations into account, we get something that ends up being quite performant. So we evaluated this now on a series of 6 distinct scientific computing benchmarks. In particular, we have DG, which is a discontinuous Galerkin kernel written in Julia, and that's run on both an AMD GPU and an NVIDIA GPU. We also have 4 other types of scientific simulations. That's a lattice-Boltzmann method from the PowerBoil suite, the Lulesh hydrodynamic solver, and XS bench and RS bench, which are correspondingly memory and compute-bound versions of a particle transport code. We then take just the run of the original program, and then we compare how the overall runtime of the both combined original program plus the gradient computes in practice. So this gradient will compute the derivative of all of the input variables, which for some of these cases can be several millions. The runtime or overhead for these is computed on the right. So a runtime of 2, for instance, means that one of the time is computing the forward pass, and the extra function call is effectively just computing the reverse pass, which is roughly optimal of what you'd like to see. So we get something that computes the derivative of all of those inputs in a reasonable, within roughly an order of magnitude of the original runtime. So now let's look how well our hypothesis again of the fact that optimizations really impact the code is. So if we were going to take the same reference style pipeline, running no optimizations first, and then plot it here, we'd see that the overall overhead of those 6 benchmarks is that 5 out of the 6 in red here immediately run out of memory and thus can't be run at all. And the one guy that succeeds at running takes 3,000 times as long, which really isn't great if you have to wait around. So we do the same thing that we did in the CPU case. We run those pre-processing optimizations. And for some of these cases, we get a reasonable enough speed up. So if we get things that tend to not run out of memory immediately, and we get up to as fast as 2.4x to 26x to, in the case of the DG here, still roughly 1000x. And again, we have 2 of these cases, the DG on ROCm and LPM, that aren't yet able to run without running out of memory. So then we apply those new AD and GPU specific optimizations we mentioned earlier. So the example of that we showed was the min cut algorithm to be able to do the cache reduction. So now with these additional optimizations, now shown here in green, we get down to that roughly within an order of magnitude runtime that we saw before. So really here, the key conclusion is that being able to do generic automatic differentiation on GPU kernels is intractable without running optimization first and running within an optimization framework. We then took the results of these and we plotted how they went ahead and scaled. So what's specifically plotted here is we increase the problem size by keeping the same amount of work per thread and thus effectively increasing the number of threads and thus the total amount of work. And then plotting how the overall overhead scales as a function of this relative problem size. So all of these cases that we tested tend to asymptote around a particular number. Some of them may eventually asymptote, such as in this case, the Julia ROCm case goes up a little bit, but for the most part, they tend to maintain the same scalability as we saw on the original code for the GPU. Overall, Enzyme is, in conclusion, a tool for performing reverse and now forward mode automatic differentiation of statically analyzable LLVM-IR. Because it works at the low-level compiler, you can have a single tool which differentiates code in and between a variety of languages, be it C, Fortran, Julia, Rust, Swift, what have you. As we showed in the first half of the talk on the CPU, we're able to get a 4.2x speedup over AD by first being able to apply those optimizations. And this allows us to get state-of-the-art performance when compared with existing tools. Moreover, we've now also demonstrated that Enzyme is the first general purpose tool for being able to perform reverse mode AD on GPUs, which by first applying those novel GPU and AD specific optimizations, we can improve the runtime by several orders of magnitude and thus make the overall problem tractable. And finally, we provide nice bindings such as PyTorch enzyme and TensorFlow-Enzyme that allows ML researchers to use foreign code inside of their existing workflow. So there's a host of people that I'd like to thank for various parts looking over the work, this presentation, and so on. I in particular was supported by a fellowship from the Department of Energy, and my collaborators and I were also supported from both DARPA and other grants from Leno and the US Air Force. Thank you so much. Any questions?
Yeah, go ahead, Jamie.
Oh, that was just me clapping. I'm very excited about this work though, so no specific questions. I need to go dig into the code some.
Sure.
Yeah, great.
Well, if you're digging into the code on our website, which is enzyme.mit.edu, we have a couple of tutorials as well as on enzyme.mit.edu/explorer, a compiler explorer instance where you can just type some small code snippets in and see what the actual derivatives computed of it would be.
Thanks, I will definitely go check that out.
Any other questions? Is there further docs online? Yes. If you go to enzyme.mit.edu, we have various installation guides, some brief tutorials on using it on a couple of different test cases, as well as in our main GitHub repos, which are linked to on the website. We have sample codes for being able to go ahead and try it out, including in a couple of different languages. So Neil asks, what plans for the future do I see for Enzyme? So there's a couple of different pieces that we're currently working on. So I mentioned since here, we got GPU AD. We've also recently done work to get generic CPU parallel AD. So we've integrated with OpenMP and MPI, and this enables us to work on any higher level tools that are built out of that, such as Cocos or Raja. From there, a couple of additional pieces that we want to look forward to, such as doing forward mode or mixed mode, automatic differentiation, which uses a slightly different algorithm with different properties, as well as being able to combine with an overall scheduler to be able to really optimize the overall both kernels and generic types of programs coming out of it. With respect to what level of maturity is the code, so it works reasonably well on most types of things. Like for instance, we've taken some types of code that spit out millions of lines of LLVM, and we're still able to successfully differentiate it. This by far doesn't mean that there aren't bugs and there aren't things that will come across when trying it out. But for simple things, it should probably just generically work. And if you have more complex things or things that are built out of it, like Boost or some other higher level frameworks, they probably should work. And if they don't, you should file an issue on GitHub and we'll get to it as soon as we can.
Yeah, so just a note on usage, if you have LLVM available, then the build takes 20 seconds maybe. It's a plugin for LLVM, and so you don't have to like use a special compiler. It's just a compiler flag to activate this plugin. So it's it's pretty convenient to use.
Yeah.
Question here, application to Bayesian inference?
Sure. So if you have a code that you want to do, say, probabilistic programming or some other form of Bayesian inference with, there are different algorithms that will, similarly, if you want to reduce the loss of the overall probability of getting the output data given the input data, that require the derivative, and you basically go back propagate through there to go and solve for the best fitting parameters within the Bayesian inference interface. We've tried out a couple of use cases of this, in particular, say taking the Julia Bayesian inference tool called gen.jl and using Enzyme to differentiate through a small part of a GPU climate model. But similarly, automatic differentiation is usable in wide varieties of applications, basically any part of Bayesian inference when you want to do a gradient update. Any other questions? Well, if not, and you come up with new questions, I'll be around Boulder for the next day and a half and am available on GitHub, email, or whatever else, and happy to walk people through using it or answer any other cool questions that come up.
Awesome. Thanks a lot, Bill. I can also help set that up. So you can write him directly or write me. And yeah, thanks everybody for coming.
Cool. See you later.